Multi-agent reinforcement learning is a common method for teaching robots in a multi-robot system how to solve a task. MARL requires a training stage in which robots can freely interact with the environment and receive feedback on actions, but this often requires a large amount of time and data. This work utilizes dialogical large language models to create plans which can guide the MARL policy by picking higher performing actions from the start of training to decrease the time required. By using LLMs, we can increase the transparency of the system. We can utilize the encoded reasoning and knowledge. It is also easier to integrate humans into the system, and LLMs can react to environmental changes faster than retraining MARL policies. MARLIN is divided into two stages. At the start of each episode, we decide whether to generate actions for the episode by either sampling the action distribution, which is the standard way MARL generates actions, or by using interagent negotiation. This depends on whether the LLMs have solved the task already, or if the LLMs are likely to outperform the actions generated by the action distribution. There is a small chance that any given episode will switch the action generation method halfway through. This is to allow the MARL policy to gather data from elsewhere in the environment and to provide the LLMs with an opportunity to guide the policy back to a good position. After this, we can simply execute the episode as normal. The robots create plans by proposing actions for themselves and critiquing the proposed actions from others. Only once all the robots agree on which actions they should all take are those actions added to the plan. MARLIN was evaluated against benchmarks using a standard MARL implementation and one using only the LLM generated plans. We evaluated 5 scenarios in simulation and 1 in real life. MARLIN trained faster than the MARL benchmark with little cost in performance for all scenarios. In simulation, MARLIN reached peak performance faster than MARL and outperformed the LLM-based benchmark across all the scenarios. These results were consistent in the real-world experiments for the maze-like corridor. The reason we chose this scenario was because it was the hardest to execute in simulation. There are several expansions we would like to explore for MARLIN, such as continuous environments and actions, systems with significantly more robots, and giving the LLMs access to robot sensor data. This paper introduced MARLIN, a novel approach for guiding MARL policies during training using plans generated through multi-robot debate. This resulted in faster training compared to MARL, both in simulation and on real hardware, with little impact to performance.